This video covers circuits. Now to finish up talking about light bulbs are sold by their wattage, which is related to the power consumption of the bulb, and we buy lights with higher wattage to get brighter lights. Now light bulbs sold in the US are intended for a 120 volt parallel circuit, and in these circuits higher wattage means brighter bulbs. However, if you were to wear the same bulbs in series and use them in a European 240 volt circuit, you would not draw the same wattage stamped on the bulb, meaning that wattage is not fixed, and that's something we need to take away from that. Light bulbs are actually resistors, and it is their resistance that follows the bulb from circuit to circuit. Now, we need to find the resistance and transfer this to each new circuit. So, let's look at the light bulbs in circuit. We have a 120 watt light and a 240 watt light that are connected to a US 120 volt parallel circuit. Well, remember that power adds, so we have 240 plus 120 gives us 360. If we know power and we know voltage, we can solve for the current and the total resistance. Now remember, for a parallel circuit, the voltage will be the same for both of them. Remember to use P equals IV to find the current. So, power is equal to I times V, so 360 divided by 120 gives you 3. Again, if you know power and you know voltage, then you can solve the current that goes across each of the resistors. So remember that the current in a parallel circuit needs to add up to give us our total current. And with all this information, we can solve for the resistance in each of the light bulbs. Now this resistance that we solved for, this is going to be a constant. This is what's going to follow the light bulbs even after they've switched orientation. So even if we turn this parallel circuit into a series circuit. So we can redo all these calculations. Again, you're going to see some of the stuff is going to change. So 120 volts, 120 as one of our resistors. Our resistors are in series, so they add up. If we know voltage and we know resistance, we can solve for current. Now the current is going to stay the same for all resistors in series with each other, so that 0.67 is true for all three. And if we know that, we can solve for voltage and then eventually power. Now here you can see that the power in series does not match up with the power printed on the bulb. Like we said, it would be 120 and 240. Again, resistance is the only thing that remains constant. So now these bulbs are connected to a 240 volt parallel circuit. This is a European circuit. Again, we can solve for the total resistance by using 1 over 120 plus 1 over 60 to give us 40. Remember, we need to find the inverse of that final number. With voltage and resistance, we can solve for current. Again, this voltage is going to be the same for all resistors in parallel. If we know voltage and resistance, we can solve for current and therefore solve for power. Again, you can see these huge differences in power when we're solving the different problems. Now, here it says, what is the same for the light bulbs no matter what circuit they are in? Again, this is resistance. The printed wattage on light bulbs is only true if used in a 120 volt parallel circuit. In a series circuit, the light labeled 240 watts actually drew half the power of a 120 watt light. Again, to avoid wrong answers, we need to make sure that we find the resistance of a light and then find the true power afterwards. Now our last part has to deal with capacitors. When we're dealing with capacitors, again, when two or more capacitors are wired together, the capacitance adds to form a sum of capacitance, or equivalent capacitance. Again, this is very similar to equivalent resistance. The equivalent capacitance is the value of the capacitor that would be needed to do the same job as several capacitors added together. Now, these equations are flipped from what they would be for resistors. Again, for adding capacitors in series, we're going to add the inverse. Make sure to get the inverse of that addition at the very end. And for adding capacitors in parallel, we simply add them together. Again, this is opposite of what you do with resistors. So let's try our first example. Here we have a 9-volt battery connected to 3 resistors. Again, we're going to add them inversely. So that's 1 over 2 plus 1 over 4 plus 1 over 4. Common denominator. That means we get 4 over 4, or just 1. So our total capacitance will be just 1. Now remember from our previous videos that our charge for our entire circuit is going to be equal to our capacitance times our voltage. So if we know our total capacitance and we know our voltage, then our total charge will be just 9. Also remember that Kirchhoff's rules still apply. So the voltage that we use up as we move around the circuit still has to add up to 9. So that means our charge is actually going to be the same for every single capacitor in series. That means this is 9, 9, and 9. Again, using our Q equals CV, that means 9 divided by 2 gives us 4.5. 9 divided by 4 gives us 2.25. And 9 divided by 4 gives us, again, another 2.25. So you can see that my 4.5 added up with those other two voltages give us a total of that 9. So let's try another one. Here we have two capacitors that are in parallel with each other, and they are in series with their capacitor. So to simplify, we can say that 2 and 3 are in parallel with each other. So if these are in parallel with each other, they will add up. So that's 4 and 4 gives me 8 microfarads. Okay, so if we get 8 microfarads for this capacitor, we can replace this with, I'll label this with C. Now this C capacitor is in series with this C1. So to add those together, I do 1 over 8 plus 1 over 8 gives me 2 over 8 or 4 as our actual capacitance. So that's 4 microfarads. So we're going to apply Q equals CV to solve for the total charge. So that's 6 times 4 is 24. Remember that charge, like current, is going to be the same for everything in series. So that 24 is our charge on our first capacitor. And then that charge is going to split for these two capacitors. But we know that if we have Q here and 8 here, I can solve for V. So that's 24 over 8, or 3. That means this first capacitor is going to use up 3 volts. And capacitor 2 and 3 are each going to use up their own 3 volts. Here we can check that 4 times 3 gives us 12, and 4 times 3 gives us 12. We can see that if we add up these voltages that we get, if we add up either one of these voltages, either this 3 and 3 or this 3 and 3, we get 6 volts. Again, my charge is 24, so if I have 24 across that first capacitor, it's going to split when I reach this junction, so 12 will go here, 12 will go here, and then those 12 will gather back together as they go back to my battery. And finally, we have RC circuits. These are circuits with both resistors and capacitors. Now, the part that we're going to focus on is a steady state. And all problems will say that you are dealing with a steady state. Another way to say that is it's been on for a very long time. So it's been on for a very long time. So when a capacitor is fully charged, it acts like a break in the circuit. And I'll show you an example of what we mean. When it's fully empty, that means that it is just being connected. It acts like a wire. Now the first example we're going to look at is a capacitor in series with resistors. Here you should notice that the voltage across the resistor decreases and the voltage across the capacitor is going to eventually reach the voltage of the battery. So here you have the FET simulation that we have earlier. Okay, I'm going to reset the dynamics. Okay, here you can see I have a capacitor and it's empty. I have no charge on it. Over here I have a resistor. Now this over here is a little graph and it's going to show the voltage across my resistor. Over here I have a voltmeter and it's going to tell me the voltage across the capacitor. Again, at the very beginning, my capacitor is uncharged. So what it's going to do is it's going to act like a wire. So let's play. Here you can see that I have a 9-volt battery. Here you can see that the voltage was initially 0 and now it's approaching 9. And you can see that it's going to slow down until it reaches 9. Over here you can see that the resistor initially started with a voltage of 9, but then started to decrease as it approached 0. So now my resistor has no current going through it. You can see that I have my current reader over here, and I have no more current going through it. Again, what that means is my capacitor is fully charged, so it acts like a break in the wire. So if there's no complete circuit, that means that I have no current flowing. No current flowing means no voltage. In this picture, I have 2 resistors, and one of the resistors is in parallel. You can see that I have a junction here. It's in parallel with this capacitor. Okay. Now I have a voltmeter that is reading a voltage across my capacitor, and I have another voltmeter that's going to show me the voltage across my other resistor. And then we'll look at this middle resistor in a second. So again, I'm going to reset all my dynamics. And then I'm going to hit play. And you're going to see that the voltage across my capacitor is going to increase. Let's see that again. Okay. It's going to increase, but now it's not going to increase to the voltage of the battery. Okay, so it's only increasing to about 4.5. That means you should expect, if my battery is still to be 4.5, then that means this resistor should be also 4.5. Again, Kirchhoff's loop rule. So that means that this resistor should also have a voltage of 4.5. As you can see that there is no more current flowing through this outer wire. So essentially these 2 resistors are acting like 2 resistors in a series. So there's no more current flowing over here. Now if I disconnect my battery, you can see that current starts to flow and discharge my capacitor. Okay. But we're not going to look at those examples. We're only going to look at the ones where we have a steady state, which means that my capacitor has been on for a while. Again, this capacitor will have the same voltage as the other resistor in parallel. And then we'll talk more about this next time.